Hello, students. We're starting a new topic, coordinate geometry. So the first section is about polygons in the coordinate plane. So what does that mean? That means in geometry, which people have been doing since ancient civilizations, the Egyptians, the Babylonians, they used to just draw shapes and look at the relationship between shapes. It wasn't until around the year 1600 that a philosopher named René Descartes, he was a French guy, René Descartes, Descartes, it's very French. There's a story that he was sick as a boy and he was stuck in bed and he was looking up at the ceiling and there was a fly flying around and he's like, ooh, I could figure out where that fly is on the ceiling if I came up with a coordinate here. He's also really famous for saying, I think, therefore I am. That was him. He's a philosopher. Back in the day, smart people did math and philosophy and, art and all of that was all together. Sometimes you will hear this referred to as the Cartesian plane. That's because they're taking this part of his name. There's another study, this cartography. Do you know what that is? It's the study of maps. So that also came from his name. If you put shapes onto the coordinate plane, now you've combined pure geometry with algebra, numbers and variables, and you get this dance floor. I like to say this is where they go dancing. All right, so once we put this triangle on the coordinate plane, what can we do with it? Well, instead of just saying we have, a triangle and, we might be able to measure it and things, we can actually use the coordinates to do algebraic manipulations. We can plug them into some formulas and they can tell us some stuff. So the first thing that we would do is we would assign coordinates for each of the points. So A is at 2, 1, 2 in the x-axis, 1 in the y. B is up at 4, over at 4 and up at 7. And C is located at 6, 3. Once you have those numbers, those are XY pairs, right? Which formulas can we use that have these sort of XY pair combinations in them? We've done some a while ago, and you will see them again as you continue along with your math. Okay, so these are all XY pairs, right? This is x2, y2, this is x3, y3. All points have an x and a y. This is the first, second, and third point. Yeah, so we can assign numbers to the points. We can look at their location, and we can also use the coordinates to find how long the side length is. So one thing we can do is we can use the distance formula to find the lengths of the sides. Okay, and once we have that, maybe we could calculate the perimeter. Maybe if we know the lengths of the sides, we could calculate the area. So let's just do this one first. We haven't done distance formula in a while. So let's say I'm looking for AC, and that's going to be the square root of the difference in the x coordinates and the difference in the y coordinates. So I'm not modeling this very well, but yeah, I'll do it. So you got x2 minus I'm going to do x3 minus x1 and y3 minus y1. So I'm doing A and C, and I already labeled these 3 and 1, so that's why I used that. So AC is going to be the square root of what's x3 minus x1. That's 6 minus 2, which is 4. Okay, you can see here, we had the 6 right here and the 2 right here, and you can see this is 4 right here. 4 units. Doop, 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 doop. And then we can subtract the y coordinates. That's going to be our change in y right here. And this is going to be 3 minus 1, which is 2. You can see right here that these are 2 apart. And then if I want to find out the length of side AC, that's going to be 16 plus 4, which is the square root of 20. And then you could leave it like that. Some of you are practicing your radical work. So this is actually 4 times 5. And 4 is, the square root of 4 is 2. So this is 2 square roots of 5. So how long is AC? AC is 2 square roots of 5. It's kind of like the hypotenuse of this little teeny tiny right triangle. Okay, so if I did that process over and over again, I could find, well, there's 2 and there's 4. So this is also 2 times the square root of 5. And this one, they're 1, 2, 3, 4, 5, 6 away. And so that would be 36, and that's 2. So that's 36 plus 4 is square root of 40. And if you wanted to simplify that, that would be 2 times the square root of 10. Okay, so I found all 3 sides. If I want to find the perimeter, I could then add those up. So you could find the perimeter, add all 3 sides. Or 4 or 5, however many sides of the polygon there are. Polygons are many-sided figures. Polygon is a Latin term. So we have Greek, Latin influences throughout our geometry class. So if I wanted to find the perimeter, I would add 2 root 5 plus 2 times the square root of 5 plus 2 times the square root of 10. This is kind of interesting. You can add these 2 together because they have the same irrational part, but you would not add this one with it. So a really good answer for this problem is 4 square roots of 5 plus 2 square roots of 10. And that's it. You would just say all of that many units. If you wanted to figure out what that was, you could go put it into Desmos and type that in and see, oh, that's a decimal. I can do that. So I'll go type it into Desmos. Been using the scientific calculator recently. It's good to be familiar with it. So I said 4 times the square root of 5 plus, oops, that's not there. That'd be over here, plus 2 times the square root of 10. Okay, so it's around 15.3, I'll round it. 15.3, and whatever these units are is what our units are. Okay, so we can use the distance formula to find the lengths of the sides. That would give us a way to find the perimeter. Okay, we could also use the lengths of the sides to calculate the area. I'm not going to do that for this one, but that is definitely a possibility. The other thing that we can do is we can try to classify. And that's what your homework is on a little bit. So what else would we want to classify this? I'm going to skip ahead here. So could we classify this triangle by its sides if we know the side lengths? Of course we can. So what do we know about our triangle? Two of them match, and one of them is different. So what kind of triangle is this? Okay, if I was going to classify it by its sides, I would say it's isosceles because two of the sides were 2 times the square root of 5. What about the angles? Could I use the coordinates? Could I use the pure math, these numbers, to figure out what kind of triangle this is? The strategy for this is to use another formula, and it's the slope formula. You guys remember that one? Okay, in algebra class, we use the letter M. And it's a formula, you'll see rate of change. You'll see it come up in a lot of your classes coming up. And this one is the change in the y2 minus y1 over x2 minus x1. Okay, so what's the slope going to do for us? Well, if I find the slope of line segment AC, since it's on this really nice graph, I'm just going to count it. I could definitely use these numbers up here, and that's what a computer program would do. It would just take these exact values and just shove them into the formula and do no thinking. And I already have it here. The slope of this line is 2 over 4. The rise is 2 and the run is 4. So I'm just going to do 2 over 4. Okay. What's the slope of line segment BC? It's negative 4 over 2. That's interesting. And the slope of AB is, so you can run these formulas on all the points on here. There's just so much math you could just keep doing, right? You could do distance formula on all the side lengths. You could do slope formula on all the side lengths. And then you could look at these numbers and say, what does that tell us about this triangle? This one is 1, 2, 3, 4, 5, 6 over 2, which would simplify to 3. Okay, so these two are related to each other. They're the reciprocal and they're opposite. Does anyone remember what's true about slopes that are opposite and reciprocal? Yep, they're parallel. Okay, opposite reciprocal slopes are parallel. We learned about that. Mean the lines are, oh, I said it wrong. Lines are perpendicular. My bad. Okay, parallel means they're the same. Perpendicular. Wow, that's not how you spell perpendicular. I don't even know what that says. Perpendicular. Perpendicular. Okay, perpendicular. So if I was trying to classify this triangle, I know that it's isosceles. I also know that this is a right angle. So I know that this triangle is a right isosceles triangle. I also know it's super special. It's a 45, 45, 90. How do I know that? All right, so we classified that one as right and isosceles. We used the slope formulas to show that the lines were perpendicular, and we used the distance formula to show that the lengths, 2 of the lengths were the same. All right, so this is one you could do, but I'm going to make the computer do it for me. So instead of doing all the distance formula and all the slope formulas by hand, I'm going to actually make the computer do it. Okay, and the way we're going to do that is we're going to go to GeoGebra and we're going to program in this triangle, PQR. So I'm going to go 4, 1, 2, 7, and 8, 5. Turning on the grid lines, and I'm going to adjust this a little bit. Okay, there is a point at 4, 1. there is a point at 2,7. Did I get that right? I think there's one at 8,5. Okay. And I'm going to make the computer do all of the calculations. It's going to tell me the side lengths, and it's going to tell me the other stuff. So I think I'll turn that into a polygon. So I'll use the polygon tool. If I was really into this, I could actually change these letters. Okay, I could, well, I could say, actually, this is letter, what was it? PQR. So this was R. Okay, that's how you would do that if you wanted to do a really nice job. Oh, now I'm just going to get into it because PQR. Apparently, I have nothing better to do with my life. QR. Okay, I hope people appreciate these. Whoa, stay there. Okay, I'm going to make the computer do it. So I'm going to say I want to know how long it is. So I'm going to click on that line segment, and it's going to tell me how long it is. And I'm going to do it again. I want to know how long this one is. Boom. I want to know how long this one is. Boom. If I open up the calculator, it's actually going to tell me, see this segment right here? You can actually see the math that it did there, but I'm not showing it at the moment. See this advanced scripting, color. This is the computer program that it's running. It's actually just doing the distance formula between those 2 points. So it'd be fun to play around in here a little bit more. I haven't done that a whole lot. So that's it. That shows me that it's what kind of triangle. It's isosceles again. These two are the same. Yeah, I can also find the slope. The slope tool is down here. I think it's in more. Okay, so slope is a really important concept in math classes. Anything on a graph, we are often looking for the slope. So it says select a line, boom, there's a line. So the slope of this line, you can see the slope triangle here is 1, up 1 over 1, up 1. I could do the slope of this line. Slope of this line is -3, and the slope of this line is -1/3 is what that is. And none of those slopes are opposite and reciprocal, which makes sense because look at this triangle. It's obviously acute. So I'm going to screenshot this so that it's in the notes so you can see how I did this problem. And something like that. So this is where algebra and geometry go dancing, right? What kind of triangle is this? This is an isosceles. The triangle is isosceles and acute. It's an acute isosceles triangle. How do I know that? Because I made the computer do the distance formula for me. All right, so what can we do with this? Well, we can also use the distance formula on this one. If somebody asked us what the perimeter is, we would do it the same way. We can also use the slope formula to find the slope of each side. So in general, if we give you a polygon on a coordinate plane, we might be wanting you to classify it. So what kind of polygon is it? And back up your thought, not just because it looks like it, even though it actually does just look like it, but why? Prove it to us, give us some evidence using the coordinates of why you believe that to be true. So the first thing to do is write out the coordinates. What is E? E is at 3, comma, 4. And F is at 7, comma, 5. And G is at 6, comma, 2. And I'll put D in front. D, E, F, G. D is at 2, comma, 1. All right, so let's just look at the slope of each. And because it's on the coordinate plane so nicely, I'm just going to straight count it. So what's the slope of this line segment right here? What's the slope of line segment DG? Well, how much up is it increasing? Rise. And how much is it running? Okay, here's our slope triangle. It's going over 4 and up 1 over 4. And we do the rise number in the numerator, okay? And then I'm gonna do the slope of line segment EF, right? It's also up 1 over 4, right? So if you showed somebody this, and then you said, I know these are parallel, and somebody said, how do you know they're parallel? You could say, well, look, they have the same slope. I just showed you that this one has a slope of 1 over 4. And I showed you that that one has a slope of 1 over 4. And I know that parallel lines have the same slope. So that helps me start to prove that this shape is a parallelogram. Okay, I just proved. So therefore, line segment DG is parallel to line segment EF. This is how you could use this in to win your argument, right? I know the slope formulas. I basically used these numbers. From D to G is 4, and from 1 to 2 is 1. There's your 1 over 4. And then I did it again with these. Yeah, from E to F is up 1, and from 3 to 7 is up 4. Okay, so I could classify that. So I showed that it's a parallelogram, right? Is it more special than that? Do we think it's a rhombus? It doesn't look like a rectangle or a square. It doesn't look like a kite. It's definitely a parallelogram, right? I could still do the distance formula and find the perimeter. I could also, maybe I could check the diagonals. I can see if the diagonals intersect at a right angle. Sometimes that would help me see if it's a kite. So that one is a parallelogram. Let's go back to GeoGebra for this one. And let's see if we can see what it looks like. So PQRS. I'm going to clear this out. Just start a new one. How do I do that? Clear all. Don't save. Okay, start a new one. So I'm going to turn on I'm going to go dancing, right, with algebra. And we're going to go over here. And it looks like they were really nice and put everything in quadrant 1 for us. And we got 2, 1 and 2, 5. I'll do those two first. So I need to point at 2, 1. And I need a point at 2, 5. Okay. Interesting. What are my other two? 7, 6 and 6, 1. 7, 6 and 6, 1. All right. So what kind of quadrilateral is this? Is it special? Can I prove it's special? Maybe it's special. Okay, so I can start to run my algebra work. I can find the distance. So what kind of shape has the two sides next to each other that have the same length? Okay, what else can I do? I can run my slope formulas. And that's slope of 0. Let's see what it does with this one. This slope is undefined, so it doesn't like to do it, so it's not going to do it. Okay, that slope is not able to see. Let's see. This slope is 5, and this slope is 0.2. Okay, these are right angle, but that's not necessarily important. So it looks like a kite to me because it has two, the adjacent sides are congruent. Okay, none of these are parallel. These are definitely form a right angle, so maybe it's a right kite. I don't know if that's actually a thing. One thing we could do is we could analyze the diagonals. So I can put in these diagonals. And with kites, this has to be a right angle in here. So I could run the slope of the diagonals. What's the slope of that diagonal? It's 1. And what's the slope of this diagonal? -1. So you can see it's down 1 over 1, down 1 over 1, down 1 over 1, down. And the slope of this one is up 1 over 1, up 1 over 1. And right here, the slopes are opposite reciprocal, so they meet to form a right angle. So I'm going to cut that, copy and paste that in. It's good to be able to use technology to do these things. So that's what it looks like. And to answer the question is, the question wasn't very clearly stated, but it's what kind of shape is it? The quadrilateral PQRS is a kite. It has adjacent sides with the same length, and its diagonals are perpendicular. And how do I know those things? I know those things because I could use distance formula on the sides, and I can use slope formula on the diagonals and show that they're opposite and reciprocal. Here's a little summary. If you're doing coordinate geometry, it's where algebra and geometry meet. Okay, you can use the distance formula to find side lengths and classify. You can use the slope formula to see if there's any right angles anywhere or if there's any parallelograms anywhere. Okay, so if it's parallel, the slopes are the same slope. And if it's perpendicular, the slopes are opposite and reciprocal. Opposite and reciprocal. And we're not going to worry about the midpoint formula very much. The big idea is that you know you can apply formulas to these things. This is kind of annoying. This is 2 times the square root of 5. All right, be good, work hard, keep learning. Come to office hours if you need help. Bye.